Dear students, today mostly we are going to compare among hydrogen halides. Of course, HF behaves entirely different when compared with HCl, HBr and HL. Of course, we find a certain relationship among hydrogen halides in their reaction and all. Before we actually enter into the comparison of the properties, we are going to compare based upon the method of preparation. So direct combination. By direct combination, we can prepare mainly hydrogen chloride. So we are going to compare the trends in the behavior of hydrogen halides. For that, we are going to start with their preparation method itself. First one, direct halogenation or direct combination, I can say. Hydrogen with halogen may form hydrogen halide. That is the concept. Usually, HCl is prepared by this method. So, okay. Fluorine reacts with hydrogen violent reaction to give HF. So, direct combination is possible for a Cl. With violent reaction, it reacts. Hydrogen reacts with fluorine. But with HCl and HBr and HI, the reaction is reversible. The reaction happens to be reversible. Therefore, it is not possible for us to prepare pure HBr and HI. So, the reaction is reversible. So, preparation of pure HBr and HI not possible. Alright. So, now we have compared hydrogen halides. By direct combination, we can prepare HCl. HF can also be prepared, a violent reaction. Okay, it can be prepared. But HBr and HI cannot be prepared because the reaction is reversible. Alright. So, by direct combination, we can prepare HCl, HF and HCl. The order goes like this: fluorine, chlorine, bromine and iodine. Violent reaction, it reacts. When it reacts, the reaction is reversible. This is how the reaction goes. Then displacement reaction. What do you mean by displacement reaction? Replacement of halogen. That is, when sodium halide is made to react with sulfuric acid. For example, sodium chloride is made to react with sulfuric acid. We have seen this reaction earlier. I think you are remembering this. When sodium chloride is made to react with the sulfuric acid, sodium bisulfate and HCl. We have prepared hydrochloric acid only by this method. The sodium bisulfate again reacts with sodium chloride to become sodium sulfate and HCl. So we can prepare HCl by this method. If we try to prepare sodium bromide or sodium iodide, of course, HF is not prepared by this method. If we try to prepare this, what is happening? Instead of producing HBr and HI, they get oxidized into bromine and iodine. So they get oxidized. Oxidation occurs. So what sort of product can be formed by oxidation? As usual, it may be formed HBr. That HBr will be oxidized by, HBr and HI will be oxidized by sulfuric acid. That reaction will be seeing. So HBr and HI cannot be prepared. Of course, the expectation is sodium bisulfate HBr, sodium bisulfate HI. But the HBr and HI formed undergoes oxidation. When they are oxidized, the product is bromine, iodine. So we cannot prepare HBr and HI by this method. Alright. So by displacement method, halides can be converted into hydrogen halide. Metallic halide can be converted to hydrogen halide. In this method, better to prepare HCl, not HBr or HI. Then, next one, third method. So, we are differentiating the properties of hydrogen halides based upon the preparation itself. Third method, preparation of hydrogen halide from phosphorus trihalide. When phosphorus trihalide is made to react with water, usually in drops, so that all the three halogen will be replaced by 3 OH. We need 3 water then. So POH thrice, H3PO3, H3PO3. Instead of 3 halogen, 3 hydroxyl group. 3 hydrogen and 3 halogen get combined to give 3 HX. So by this method, all the hydrogen halides can be prepared except HF. Here, PCl3 can be made to react with water to give H3PO3 plus 3 HCl. Or else phosphorus can be made to react with chlorine. Phosphorus can be made to react with chlorine or bromine or iodine. Usually, HBr and HI are prepared by this method. Phosphorus can be made to react with bromine, and during that course, drop by drop we are adding water. Water is added drop by drop. What is happening? Phosphorus reacts with bromine to give PBr3. It forms PBr3. How to balance the equation? 3, 2. Therefore, I can write 2 and 3, but it is P4. If I write P4, if it is 2P, I can write 2P, but usually we write P4. In the book, they are given only like this: 2P plus Br3Br2 gives 2PBr3. Nothing wrong. But if I write P4, it has to be 6Br2 gives 4PBr3. It can be written both ways. This or this. Anyhow, we are getting PBr3. If we like to write phosphorus only as P4, red phosphorus and bromine, it has to be written as P4. We get PBr3. The PBr3 then undergoes hydrolysis to give H3PO3 and 3HBr. Likewise, you can get HI. HI can also be prepared by this method. HI, HBr, except HF. HF cannot be prepared by this method. HCl, HBr and HI can be prepared by this method. By the reaction of a paste made of red phosphorus and bromine. A paste made of red phosphorus and iodine. So a paste of red phosphorus plus bromine or iodine. Into that we are adding water drop by drop, so that it undergoes hydrolysis to give phosphorus acid and HBr as well as HI. So that is the difference. We cannot prepare HF by this method. Then from covalent hydrates, fourth one, it is third one, fourth one from covalent hydrates. We can start with hydrogen sulfide when it is made to react with, say, halogen, any halogen. We may get 2HX plus sulfur. This method is especially suitable for chlorine. Alright. HCl can be prepared by this method. When hydrogen sulfide is made to react with chlorine, you will be getting HCl plus sulfur. Likewise, any alkane, for example, methane, when made to react with chlorine, this reaction very common. We have seen even under chemical properties of chlorine. Substitution of hydrogen by chlorine. Step by step, methyl chloride, methylene chloride, chloroform, carbon tetrahydride, likewise it will happen. It is obtained as a byproduct. Of course, we need methyl chloride, methylene chloride, chloroform, carbon tetrahydrocarbon, and HCl is obtained as a byproduct by the reaction of alkane with chlorine. Any alkane, methane, ethane, for that matter, anything. Mainly HCl is prepared by this method. All right. So that is about comparison based on the reactions. All right. Now let us go into the next step. We are comparing hydrogen halides only. HF is entirely different. HCl, HBr, HI we are comparing. In most of the cases, all those things can be prepared. Now, the next one, maybe fifth one I can say. The hydrogen fluoride bond is strong. Almost all the hydrogen halides are gases and they can be easily liquefied. When the gaseous hydrogen halide is allowed to go with moisture, we get liquid form of hydrogen halide. White sublimation is formed due to the formation of HX in the form of liquid. So by this way, almost all the hydrogen halides can be converted into the hydrogen halides. And among these hydrogen halides, HF is having strong bond because of high electronegative nature, high electronegativity. Therefore, strong hydrogen bond. Hydrogen bond is possible only with more electronegative elements that we are aware. Fluorine, oxygen, sulfur, only these three elements seems to be more electronegative because if we go in the period table, second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And the next one, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. The more electronegative elements are being these things. Oxygen, nitrogen, not even sulfur, nitrogen, oxygen, fluorine. So these elements mostly form hydrogen bonds. Extreme right and top in the period table. Of course, next to that you will be getting neon, here helium, the noble gas, and therefore they cannot be electronegative. They don't have the tendency to attract electron. But in the first period, very small size and requirement of electron, more electronegative, little bit less, little bit less. All the three are more electronegative. All the three can form hydrogen bonding. And therefore, whenever we have compounds with nitrogen and hydrogen ammonia, compounds with oxygen and hydrogen water, compounds with hydrogen and fluorine, they form hydrogen bonding. So HF forms a very strong bond due to hydrogen bonding, high melting point or high boiling point. It has got high melting point high. Boiling point is also high. Why? It is because of the high electronegativity. It is because of hydrogen bonding, strong HF, and therefore they have high melting point or high boiling point. But of course, all the hydrogen halides can be converted to the liquids by with the moist air. All right. Then next one. So each and every point you should carefully understand. Only then for multiple choice questions, even those points may be useful for competitive examinations and all. Next one. Among HCl, HBr and HI, except HF, all are said to be strong acids. HF is a weak acid. It is a weak acid, but it has got certain peculiar property. It is a weak acid. HCl, HBr and HI are strong acids. They can easily give off they can get ionized, and therefore they seems to be strong acids. But HF, if the strength become higher, it is weak acid if it is 0.1 molar. 0.1 molar HF is weak. But when the concentration become higher, of the order of 5 molar and 10 molar, very high concentration, 5 molar HF or 10 molar HF, very high concentration. Usually we take very dilute solutions. Here dilute solutions are stronger, whereas in HF, only this concentrated solution seems to be very stronger. Why so? In the concentrated solution, what is happening? HF get combined with water to become H3O plus, hydrogen with water, H3O plus, plus F minus. Hydrofluoric acid with water becomes hydronium ion, of course reversible reaction. The F minus again combines with HF to become HF2 minus. It is also reversible. This peculiar reaction is possible only in the case of hydrofluoric acid, maybe in the form of dimerization. With the salt, say, with the sodium hydroxide, it can form the salt. It can form the salt NaHF2 with sodium hydroxide. It can form the salt. That means it is a strong acid. At very high concentration, it acts as a very strong acid. Therefore, with sodium hydroxide, potassium hydroxide, it can form ammonium hydroxide. It can form NaHF2, KHF2, NH4HF2 with the potassium hydroxide, with sodium hydroxide, with ammonium hydroxide. So it forms these sort of salts only under high concentration. During high concentration, it is because of the formation of fluoride ion and formation of HF2 minus ion, it is more acidic. H plus ions are generated. It becomes more acidic only at high concentration. All right. So HF reacts with silica. The peculiar property of hydrofluoric acid is that moist HF, moist HF, not dry, reacts with silica. Silica means silica of glass, I can say, silica of glass. To form silicon tetrafluoride and water, 2H2O. 4 fluorine, therefore 4HF, 2H2O. That HF can also react with sodium silicate. It is also a part of glass. Glass is made of silica with metallic oxides. So many metallic oxides. Sodium oxide, potassium oxide, calcium oxide, lead oxide, etc. There it exists in the form of several silicates. It is sodium silicate. Maybe considered as glass. It reacts with hydrofluoric acid to form. Of course, all the hydrogen present here are converted into water. 3HF, I can say. All right, sorry, 3H2O. Therefore, 6HF. He will be getting Na2, Si, F6, sodium fluosilicate. Silicon tetrachloride and therefore sodium fluosilicate are formed. It is a peculiar reaction for HF. No other hydrogen halide reacts in this way. All right. Only HF reacts with silica and sodium silicate to form silicon tetrafluoride and the sodium fluosilicic acid. Even hydrofluoric acid reacts with glass. Most of the reagents are kept in glass, but HF, especially moist HF, when it is kept in glass, it will corrode, it will etch glass, and it is used for the purpose of etching. All right. Then, next to that, regarding mainly iodide, HI. Under oxidation property, we should see HI. HI acts as a very good reducing agent. Don't forget. HI acts as a very good reducing agent. It gets oxidized easily into iodine. Iodine, I2. So remaining hydrogen. So 2H plus iodine plus 2E minus. It is because of the production of E minus. It acts as a very good reducing agent. HI is a very good reducing agent. HI acts as a reducing agent. Alright. HI is a very good reducing agent because it is being oxidized. Not only HI along with acid or sodium halide along with acid, what is happening? It becomes HI, but the HI get oxidized into iodine. Therefore, it acts as a best reducing agent. Therefore, by this method, it is not possible for us to prepare HI. That's what we have discussed earlier. When we treat sodium iodide with sulfuric acid or HI with sulfuric acid, iodine is liberated because it is getting oxidized. And we can test the formation of iodine using starch solution. With starch solution, iodine gives blue-black color. And what is the reason for its reducing property? In what way it behaves? For example, when HI is made to react with sulfuric acid, what is happening? Usually with other halides, it becomes sulfur dioxide. But here, HI is oxidized to iodine. The sulfur present in sulfuric acid, it is converted to hydrogen sulfide and water. Hydrogen sulfide and water. All the 4 oxygen will become 4 water. All the 4 oxygen will become 4 water. So how to balance the equation? 4, 8 plus 2. 10 hydrogen we have. Here 2. Remaining 8 should be here. 8 iodine, therefore 4 I2. So it is the peculiar property where HI reduces sulfuric acid into H2S, hydrogen sulfide. Whereas if we go in for HBr, if at all, it may become iodine, sulfur dioxide and water. Sulfur dioxide and water. So if SO4 becomes sulfur dioxide, loss of 2 oxygen, 2 H2O, 4 hydrogen, here 2, Br. So with HBr, we are getting sulfur dioxide. With HI, we are getting H2S. So HI is a very efficient reducing agent, unlike HBr. So HBr difficult to oxidize, and it can reduce, but very slowly it can reduce. Sulfuric acid is converted into SO2. Therefore, HBr can act as a reducing agent, but a very mild reducing agent we can say. But HI is a very good reducing agent. That is so important. Only HI is a very good reducing agent. It reduces ethyl, any alcohol into alkane. Decomposition, iodine will go off, hydrogen it reduces. So it reduces alcohol into alkane, and then nitric acid into nitrous acid, nitrogen dioxide into ammonium ion. All these things show that HI is a good reducing agent. HBr can act, but slowly HCl cannot act as reducing agent at all. Alright? So that is about special property of HI, reducing property. And special property of HF, it reacts with silica and sodium silicate to give silicon tetrafluoride and H2S, hydrofluorosilicic acid. So those sodium fluorosilicate with silica, it forms silicon tetrafluoride. With sodium silicate, Na2SiF6, it forms with sodium silicate, it forms Na2SiF6, sodium fluorosilicate. So those reactions are possible only with HF we have seen. Now, finally let us consolidate the reactions. What are the things? Reactivity with hydrogen. Fluorine violently reacts with hydrogen. Reactivity with hydrogen. With H2. Fluorine reacts violently. Chlorine reacts and bromine and iodine. Reversible reaction we have seen. In the preparation we have seen, by direct method these two can be prepared, these two cannot be prepared because it is a reversible reaction we have seen. And the next one, stability. Stability of hydrides. HF seems to be least stable. Stability decreases in the order. HI is a reducing agent, it gets decomposed. Stability less. HF stability more. So HF greater than HCl, greater than HBr, greater than HI. This is the order of stability. HI get decomposed, it acts as a reducing agent. Here, what you say, the bond dissociation energy is high. Bond dissociation energy is high for HF. And therefore, naturally, the ionic nature of the bond is higher here. It is going on reducing, and therefore it is strong bond, little bit weak, little bit weak, little bit weak. So stability goes in this order. HF greater than HCl, greater than HBr, and greater than HI. And then volatility. That means tendency to become vapor. HF, HCl, HBr, HI. So HI can become vapor very easily. The tendency to become vapor form is less in the case of HF. HF become liquid easily. And HI will get vaporized very easily. Volatility and boiling point may be higher for HF and lower for HI. Therefore, it becomes vapor easily. And HF, it cannot be volatile easily. Then thermal stability, same thing. Stability as well as thermal stability, stability as well as thermal stability, same thing. But in the book it is given a little bit wrongly that you refer. Stability is high for HF, lower. Stability goes in this order. HF greater than HCl, HBr, HI. HF seems to be more stable. And this order is given wrongly in the book. Just refer. And then acidic nature increases from HF to HI. Acidic nature. HF less HCl, HBr, HI. So that is about comparison of hydrogen halides. With that, we end up with hydrogen halides. All right. Thank you.